Dear students, this is an interesting problem. I chose this problem because it has a constraint relation usage, but if we go with a normal approach, there might be a chance where you might get stuck and get into kind of mathematical equations which you might find it difficult to solve. So let me just go through the question once and let's try and solve this one. So we have four identical rods are hinged at their ends to make a parallelogram ABCD. The hinged joint A is rigidly attached to a wall and the opposite joint C is pulled away from the wall with a constant acceleration A as shown in the figure. Initially the joints A and C were coincident. Find acceleration vector of the joint B as shown in the figure, okay, or the instant which is shown. Dear students, here already they have given x and y axis, so it's better if we choose a coordinate system location, so it becomes easy for us to find out acceleration of the point B. So here this is our acceleration of the point B. We need to find this point's acceleration we need to find. Now if I choose this as our origin, then it is given that our horizontal direction is our x-axis and vertical direction, this one is our y-axis. Okay, suppose if I drop coordinates for B as x comma y, we know that from here all the way to this point it is going to be x distance, and from here to this point it is going to be y distance. Okay, and from symmetry we can easily recognize that if this overall angle is 2 theta, this angle is going to be theta. Fine. And since we have this usual constraint relation, if from A to B, if its length is L, suppose if A to B's length is L, then we can write from constraint relation that L squared will be equal to x squared plus y squared. From Pythagoras theorem, or basic constraint relation, we have this one. Now since they are all rigid rods, L is going to be constant. Now we'll see, like, as we pull point C, B and D are getting closer to each other and L is going to be constant, so as x changes even y have to change, and we can easily get the relation among them by just using calculus. Suppose if I differentiate this once, I'll get 2L dl by dt. I'm differentiating with respect to time, so we have 2x dx by dt is velocity along x-axis plus 2 times y dy by dt is velocity along y direction. I'm using here vx equals dx by dt and vy equals dy by dt. So using this, we can easily observe that dl by dt is going to be 0 because L is constant, and we can solve for vy. So vy equals minus of x by y times of vx. So let me name this as equation 1 and we'll see if we have any use for this equation. Okay. Now to connect with the given information, let me check out this one. They have given this point C is moving right side with an acceleration A. If point C is moving with an acceleration A, from our coordinate system approach, we know that if I give some coordinates for point C, suppose let's say point C has coordinates x dash comma 0, then we know that from point O to C the distance, or point A to C the distance is x dash. So x dash is equal to 2 times of x. So dx dash by dt, meaning rate at which dx dash is changing, is going to be 2 times of dx by dt. And if I further differentiate this, d squared x dash by dt squared is going to be 2 times of d squared x by dt squared. So in the question they have given d squared x dash by dt squared as acceleration A, and it is constant, it seems. If this is constant, then we know that this is acceleration of the point B along x-axis, right? So acceleration of the point B along x-axis is given to be a by 2, and we already got one of the component for this question. Okay, so meaning if you want to express in vector format, acceleration of the point B along x-axis is a by 2 times of I cap. We already got this one. Now what is left? We need to find acceleration of the point B along y direction. So for that, we already have equation 1. We have to further differentiate that. So for that, I'm going to take it to the next slide. So we can observe velocity along y direction is given by minus x by y times velocity along x direction. That's what we got from equation 1, right? Now, this is something interesting. You should be paying attention here. Suppose if this point C is moving with an acceleration a, we know that point B is moving right side with an acceleration a by 2. So they have given in the question that initially point A and C were coincident. If A and C are coincident, right, then x whatever we are defining here, right, meaning which is x coordinate of point B, that was 0 initially, and it is suffering constant acceleration towards right hand side. As it is undergoing constant acceleration towards right hand side, we can use kinematical equations now, and we can write here v along x-axis, vx at any instant is equal to initial velocity along x direction was 0 because a and c were coincident, squared plus 2 times of acceleration along x direction, which is a by 2, and x is the distance covered by the point B towards right hand side. So we can easily observe that Vx is going to be root of a times of x. So using equation 1, which we are writing here, this is equation 1. Let me say this is equation 2. Using 2 in equation 1, we can further simplify this. Vy is going to be minus x. Vx value is root of ax by y. Now it is in a configuration where we can easily simplify. It is 3 by 2 here divided by y. Now it is easy differentiation. I hope you can easily go ahead about this finding acceleration along y direction from here on. So if you differentiate this equation, we have minus root a constant. Using quotient rule, denominator differentiating numerator, 3 by 2 x power 1 by 2 here, and velocity along x direction, minus numerator value differentiating denominator, which is going to be v dy by dt, which is vy, whole thing divided by denominator squared. So acceleration along y direction is going to be minus root a, and let me supply this y squared in the denominator inside. It is going to be 3 by 2 x power 1 by 2 as it is, one of the y getting cancelled out. Vx value, we have Vx value as root of a times of x power 1 by 2. I'm just writing the value of Vx here, minus, already we have x power 3 by 2 here. I'm supplying this y squared inside, and value of Vy. Value of Vy we already have. It's going to be minus x by y times of Vx. Vx value is root of ax. All these things from equation 2 and 1. Okay. So solving further, we can simplify here as minus root a 3 by 2. This is going to be x by y. Let me take this root a outside and call it as just a, and minus, this is x power 3 by 2, and simplifying it further, like this is root a, I have taken it outside. It is x power of 3 by 2 plus 1 by 2, so it is going to be just x squared, or let me just directly write x cube by y cube. You can simplify as you can easily observe this one here. Now we got all the parameters in terms of the variables which we have defined. Now we have to express our answer in terms of the given variables. So in the question they have given here, if you observe, like if this is our x and this is our y, then we can observe that tan theta is going to be x by y. So here acceleration along y direction, now we can write acceleration along y direction is minus a times 3 by 2 times of tan theta plus tan cube theta. So we are expressing the acceleration along y direction in terms of given parameters here. So I hope that's it. We got the acceleration component along y direction as well. So our x component, y component we got. So we can summarize here. Suppose if I name this acceleration as equation number 3. So this is going to be equation number 4. Using equation 3 and 4, we got the acceleration of the point B. So dear students, this problem might look simple. The problem occurs if you have chosen like constraint relation in terms of theta, and if you try to differentiate, then you have to take the component of centripetal acceleration. So it might be difficult. So I hope this helps you if you are getting stuck while solving this problem. Thank you everybody, and if you have still doubts, feel free to type in the comment section. Thank you everyone.